Welcome back to day 2 of Advances in Battery Research 2024. I'm Heather James, Conference Producer at Technology Networks, and I'm pleased to introduce our opening session for the day, ReCell, Working to Advance Battery Recycling. I'm incredibly pleased to welcome our first speaker of the day, Jeffrey Spangenberger. Jeff is the Materials Recycling R&D Group Lead in the Applied Materials Division at Argonne National Laboratory. His group works to solve material separation, recovery, and recycling challenges, resulting in cost-effective and environmentally sustainable processes that are then transferable to industry. Jeff is also the director of the ReCell Center, an advanced battery recycling program funded by the Department of Energy's Vehicle Technologies Office to evaluate and advance the cost-effective and sustainable recycling of end-of-life batteries. A warm welcome to you, Jeff. Following the presentation, we will also have a Q&A session, and we welcome any questions that you may have. Please ask questions using the Q&A system to the right-hand side of the video player. Without further ado, I will now hand over to Jeff to begin his presentation.
Hello, thank you. And thank you for giving me the opportunity to speak today. As was mentioned, my name is Jeff Spangenberger from Argonne National Laboratory. I'm going to talk today about ReCell, which is a collaboration funded by the Department of Energy. And it includes 4 national laboratories, Argonne, NREL, Oak Ridge, and INL. And also 4 universities we work closely with: Michigan Technological University, UC San Diego, Tennessee State, and Worcester Polytechnic Institute. So I'm going to talk about the work that ReCell is doing to advance battery recycling. And I want to start by taking us to the root of why we're doing all this. Batteries help decarbonize the world. Some of this may be redundant to folks, but I want to make sure that we set this up properly for why we're doing what we're doing. So batteries allow us to use more renewable energy. It allows us to power our cars with less carbon being emitted, and so we need to, and as you'll see through this presentation, we need to make sure that we take care of the resources to make all these batteries, lithium-ion batteries specifically, to make these batteries capable of being used and reused and used. I'm going to start by something that the Department of Energy has. This is basically in the green center. The goal is to enable lower cost lithium-ion batteries. To do that are the pie pieces that go around it. Real quickly, there's one way to lower costs is to find new battery chemistries that are cheaper to make. Another is, let's see, the battery recycling prize that's in red. That's a program that the Department of Energy uses to lower the costs of the infrastructure associated with battery recycling, transportation, things like that, collection. The gray wedge is what would fall under the bill or bipartisan infrastructure law work, and this is to really scale up and industrialize basically all of the processes required to recycle batteries. And then there's ReCell, the yellow wedge, and that is all about battery recycling and advancing battery recycling. Focusing on the United States. This is the Department of Energy, Vehicle Technologies Office, and so the goal is to enable the United States to make sure we have our resources that we need. Another real quick one that I want to talk about is different types of batteries, different types of chemistries. So lithium-ion batteries is a group of battery systems that have different cathode and anode, and I'll get into that a little bit in the next slide. But there's pouch cells on the left, there's prismatic cells, which are the red in the center up top, and then cylindrical cells. These are all put together, typically one type or the other is put together into a series of batteries or parallel batteries to make up a module. And that module can then be put together into making a battery. So, so there could be a lot of thousands of cells in a battery, or one battery, one cell could be a battery. Um, Down at the bottom, there is different cathode materials, except for lithium titanate, it's an anode. And then the chemistries that go into them. These are just the abbreviations for what's next to them. And then some of the applications. This isn't one plays all on this, but it gives you an idea. LCO, lithium cobalt oxide, is really used mostly in our phones and laptops. That's because it's a fairly expensive, but it's a high performing chemistry. You probably wouldn't want it in your car today. It would boost the price up quite significantly. Cobalt is one of the most expensive materials that goes into a battery. If you don't see a C in the abbreviation, it doesn't have cobalt. Cobalt helps the battery perform really well. But if it doesn't, that also means, and I'll get into this again through this talk, is if there's no C in the abbreviation, it's a lower material value. And so that makes batteries cheaper, but it also makes it tougher to recycle. So what is in a battery? You have, as I mentioned now, the anode and the cathode. The anode is typically graphite. Sometimes, most of the times, there's additives that go into them. The cathode is the chemistries that I showed on the previous slide. And then each of those, the anode and cathode, the anode is on a copper foil and the cathode is on aluminum foil. Kind of mixed in is electrolyte, and that allows the lithium to move from the cathode to the anode. And the separator prevents the anode and cathode from touching. That would be a short circuit, and that creates a lot of heat, and you have a flammable electrolyte, and then you have a fire. Let's see. When you make a brand new battery, basically all of the lithium is in the cathode. And when you first charge it, it transitions the lithium. You're using a charger to electrons to push the lithium from the cathode side to the anode side. And then when you want to discharge it, you put a circuit that does not have the push of a charger. And the lithium wants to go back to the cathode. It's pushing to get back to the cathode. And so you allow it to do that. And you can use that energy as it goes back to the cathode. And so the lithium ion goes back and forth. There's no lithium metal in a lithium battery, whatever they choose. On the right of this, you can see this is a typical, I feel like I shouldn't have put down to the ones level pounds, but it shows you an approximate amount of what materials are in a battery. And with that, when you have a lot of batteries, and a lot of weight goes into those batteries. The previous slide I showed was for a 100 kilowatt hour NMC 622 battery, if that means anything to you. So a car battery, a long range car battery. If you have a lot of cars with those batteries, we need to dig deep. The chart here on the right shows how much we need for global adoption. And this assumes an NMC 622, which is a common chemistry, with a 100 kilowatt hour battery and 1 billion electric vehicles worldwide. So lithium, we need 10,000 kilotons. The world reserve is 22, so we're at about half. The US has 750. So we don't have much of the lithium located in the grounds within the United States. Nickel, we have even less, and we need even more. We need 52,000. Again, it's about half, 95,000 kilotons. Cobalt is the interesting one. We need 17,000. The United States essentially has 0. And the world reserve is a little over 7,000. So we need to recycle the batteries. That's one of the reasons we need to recycle in order to get that cobalt back. There's a lot of work today to get rid of the cobalt use, but it makes a big difference, but it doesn't make that big of a difference. We still need so much cobalt because we're making more and more batteries, even though there's less cobalt in each battery. So I want to make it clear that we can recycle today, and we do recycle today. There's two basic process types. There's hydrometallurgical, and there's pyrometallurgical. In hydrometallurgical, you dissolve the metallic contents of the battery and then individually precipitate out. Actually, first you filter out the non-metallics so you can get the graphite out and other materials, like contaminants. And then you can precipitate out or otherwise separate the different metals as metal salts. And then those metal salts can be remade into new batteries over and over. It's not like recycling plastics where there's a degradation. We're going down to ions. And so they're always the same, and you can always make a new battery, just like it's brand new. Pyrometallurgical recycling is where you use heat to break down the metal components and burn off or oxidize the non-metallic or inert materials. Then you get a really nice clean alloy with all the good metals, most of the good metals, I should say. And then that alloy actually is used, or is processed through hydrometallurgical processing to dissolve and separate into nice, clean metal salts to make new batteries, or potentially be used in different applications. One of the challenges with pyrometallurgical is that not all of the metals report to the alloy. Some report to the slag, which is an oxide. It's difficult to get the material back. And lithium, unfortunately, and aluminum are included in that fraction of slag. So, to talk more about the ReCell Center, the real purpose is to foster the continued improvement of cost-effective, environmentally sound processes to recycle these lithium-ion batteries. As I said in the beginning, we're trying to advance battery recycling. We always improve. We are driven to improve things, reduce cost, make products better. What is it? Bigger, better, cheaper, right? For reasons that I'll tell you shortly, we research and develop at great length direct cathode recycling. That would be the third recycling process type, and I'll get into that in a little bit. We also like to bring people together from all around the country and all around the world to share their piece of the puzzle. They may be working on a new technology or a new idea. And so we like to connect people. Not one person is going to fix this and continually do the best work. It's going to take everybody that's working on this. And so we like to bring people together. The outcome, all great stuff. Use less Earth's resources, reduce energy consumption, increase national security. So if we're relying on other countries for materials, that puts us at a precarious position. And recycling can help bring the cost of a battery pack down. It makes a lot more sense that if you're going to get your materials from a pile of batteries that's filled with those materials than digging through dirt or taking materials from brine. And the last thing I didn't mention is providing stability of the supply chain. So sometimes prices go up and down on the markets. That can play into the scenarios with battery supply chain. So the ReCell Center has 4 focus areas. Direct recycling, we have 26 projects there. Advanced resource recovery, and let me take the opportunity to talk about direct recycling. Reading what's written here, this is our definition. Recycling materials back to their original purpose without destroying their chemical structure. As I mentioned in hydro and pyro, the cathode, all the metals are broken down into their ions, basically, or their metal cathode. And that destroys it. And I'll tell you on the next slide why that's not the best thing to do. It would be advanced resource recovery is where we're recovering materials that we can't directly recover, directly recycle. Designed for sustainability, is working toward more sustainable batteries. That could be by material choice, battery design, or trying to improve second life opportunities. And modeling and analysis. These are critical to the work. They help us move forward, understand, and otherwise improve. And actually, it guides the projects that we do in ReCell. We always analyze each project to make sure that it makes sense on why we're doing it. So these are the three methods that I talked about: pyro, hydro, and direct. The graphic in the middle is not perfect, but it's something that I use a lot. And if you think about it, pyro, you're gonna take at the end of life where the green line starts in the circle down about what is that, 4 o'clock, and then you're gonna take it down to a metal, and then you have to refine that metal, and that could be refining, could be the hydro process, or it could be something else. But basically, you're taking it back closer to the mining, closer to the mining part of the process. Where if you mine, you're going to dig it in the ground or whatever. You refine that, and then you make a cathode, and then you make a battery, and then you use that battery, and then hopefully you recycle it or get a second life in there too. Hydro, you don't have to do quite as much work because you don't have to go through kind of two process steps. So what you're coming out with are the metal salts. In that case, you're going to make your first step on the original blue line is you're going to make cathode with those salts. And you manufacture batteries, use the batteries, and so on. Direct recycling, we haven't destroyed the cathode. And so when you do that, you can take the product of the recycling process and put it right back into a battery. You don't need to make battery cathode. And the reason why that's so important and why we're so interested in trying to tackle the challenges associated with it is because if you look at the chart on the upper right, the blue bars are the price of the materials going into a battery for whatever unit. And the red is the price of the cathode. So the difference between the height of the red and the height of the blue is the manufacturing costs to make cathode from raw materials. So if we already have cathode, and if we look at the NMC on the second from the left, let's call it half. You can save half of the costs to recycle it back into a cathode material. If you look at LFP, you can actually see, because the materials are so cheap, that you're going to save a lot of money not having to make it into a cathode again. So that's why it's so important. That makes it a very big potential difference in cost and environmental impacts and recycling back into cathode material. Okay. So sticking along the lines of direct recycling now, we want to minimize contamination. Oh, let me say the graphic on the right. You need to have a seamless, excuse me, a seamless chain to have a process. So you need to, and this is not necessarily the right order, but you need to shred the battery, you need to get rid of the electrolyte or recover it or do something with it. You need to separate it out. You need to separate your cathode and your anode and your foils and any other metals that might be in there. There's a cathode material, black, carbon black rather, and a binder, typically PVDF, that need to be separated in many cases, and or removed is the next step. And then because a battery fails in part because it doesn't have usable lithium to go back and forth, you have to re-lithiate it. Another big challenge is it's old chemistry. You have a 15-year-old vehicle with 15-year-old battery chemistry, that's not going to cut it today. And so you need everybody needs to, if you want to reuse it in a vehicle, upcycle that cathode to make old cathode perform like new modern cathode. Then we make our new cathode, and then we can make our new batteries and so on and so forth. So one of the things that we need to do is minimize contamination in the black mass, which is the active cathode and anode powders from the pre-processing step. We recover as many materials as possible. Obviously, we need to keep costs low. We need to reduce waste streams because that costs money. That goes along with keeping costs low, and it's also tougher on the environment. We need to understand the role of the remaining contaminants, develop solutions to problematic contamination, and develop multiple solutions to increase the likelihood that a complete working process can be developed. And what I mean by that is we need to have more than one electrolyte recovery method and cathode anode separation. Because if it turns out that it doesn't work, it's undesirable for some reason, we have something to backfill that hole, because you can't have a break-in chain. So this is a picture of black mass on the left. This is with a state-of-the-art system. If you look at it, just to point out, we have, you can see some contaminant in the left picture. If you screen it, and this is a larger fraction, looking under SEM, you can see that there is, and this again, it's a larger fraction, so it's not always this bad. But you can see non-cathode. Cathode is like the balls, nice round balls. But this has streamers and odd shapes, and those are contaminants. So one of the things we're looking at is different ways to make cleaner black mass. So we looked at the difference between hammer milling and shredding, shear shredding. The shear shredder is on the upper left picture, the hammer mill is on the lower left. And you can see in the pictures, they come out different. The hammer mill is in the middle, in the blue. And really the hammer mill, you see fines, the y-axis is fines. You see that there's more fines generated in the hammer mill. And that's what you want to do, because you basically are braiding the active materials off of those foils that I talked about. So we wonder if there's a better way to do it, because when you grind up and you abrade and you beat everything up, and there's going to be those contaminants in it. And so what we ended up looking at doing was shear shredding, instead of, and carefully, putting a lot of thought and engineering into it, shredding the material. And then you have these, as you can see in the pictures, kind of squares. And the active materials stay on the foils. The first pass, you're going to generate some fines, and that's another thing you can see, but it's very low on the lower left, for example. And so you don't have, or you screen out those fines, and then a lot of the contaminants originating there are gone. Now you need to separate the anode and the cathode, and we're doing, again, several ways to do this. This is just one way. This is using a magnet, a very strong magnet, but a magnet that you can see. And this, the work here is actually about checking the sizes and how it affects it. But the smaller, the better. So the smaller, the more fines you're going to generate. With a 1/4-inch electrode, so 1/4-inch square, you can see the color difference. One is going to be the anode and one is going to be the cathode. And you can see how effective that separation is. The problem is now, how do you get it off? And so here is, again, just one opportunity to do that. On the left are squares of an electrode. And Oak Ridge has actually come up with a solvent that we call Solvex, that you can put on the foils or the electrodes, and the active electrode material actually falls off from the foil, and then you can redissolve it and cast a new electrode, essentially, and it works really well. So that's one way to get the materials back, and very clean. Those are just a couple of projects that we talk about. There's plenty that we tackle. To mention a few, in direct recycling focus area, we look at the cell pre-processing, like I just mentioned. We look at electrolyte recovery, binder removal, anode cathode separation, cathode separation if you have different chemistries mixed together, relithiation, anode recovery, upcycling of those recovered cathodes and impurity effects. For advanced resource recovery, we have hydromet that we work with, pyromet that we work with, and electrochemical metals recovery. Again, this is just well, several, but not all of them. Design for sustainability, we're looking at reuse of materials, second life, batteries, and disassembly techniques. And in modeling analysis, actually, I'll talk more about that, but I'd like to make sure that I mentioned that we have Everbat, which I have some slides on. That's a cost and environmental calculation tool for recycling. And then there's also a supply chain model that NREL leads with, it's called Libra. So we got all that out. Now, the main objectives from 2019, which is when ReCell started, to 2022, which was a good place to make a cut and start some new goals. But we needed to get this collaboration together. We need to assemble it and all that from the beginning. We need to get the word out. One of the important things is we work very closely with industry. It's so important because if they're not going to take the lead on something we start, then there's not much, there's definitely value, but not as much value in doing that work. We had the focus areas, which were a little bit different. I won't get into that. Mostly bench scale tests were being experimented with. People had new ideas and testing new ideas. We review each project in Everbat. And then some of the more promising technologies that were a little bit more further along, we scaled up. And then we demonstrated that direct recycling cathode from end-of-life batteries can actually be done. Some people said, you know, it's not going to work, or it's not going to work well. And so we put together a real test to just demonstrate it. It wasn't messy. No, it was messy. It wasn't clean and simple. We went from one bench unit to another to go through the stages to make that material and make new batteries and testing. And you can see on the second bullet here, we actually did get 175 million per gram from a 622 recycled chemistry. We generated over 20 inventions and over 40 publications. We don't hide too much. We're trying to help the United States. And so we get the information out there, which is kind of nice. You know, we're not a business. We're not trying to make money. We're basically a nonprofit. And so the objective is to help other people succeed. Also, manufacturing scrap is a great opportunity for direct recycling. So we've looked at that closely. It doesn't have as many of the challenges that we have when we do end-of-life batteries. The big example is it's not 15 years old now. It's brand new. And sometimes it's really not even the whole battery. It's just part of the battery. It could be an electrode that wasn't running up to spec or whatever it is. And so we can rework it and put it right back on the front of the line. So the main objectives in 2023 and beyond is to continue growing the collaboration, obviously, and continue engaging with industry. We did update the focus areas as to the way I described it in the beginning. But we're really excited about adding about 12,000 more square feet to our research space. I have a drawing on my next slide that'll give you an idea of how much more that is. That's going to allow us to install a pilot scale plant for research purposes, not just to run all day and night. It's really so that we can test different unit operations at pilot scale. And we did the demonstration of direct recycling. We want to do a larger scale demonstration now. And we'll focus on manufacturing scrap first. So on this one, the expansion, you can see on the lower right that the blue was the current high bay space. We have 2 more labs, but then the big add is this green that's on that chart. So that's the 12,000 square feet that we're adding. Right now, it's under construction, so to speak. They're prepping the space, making it more versatile for the space that it was. And this is actually exciting because we can now work closer to industrial scale, because you can't just go from bench scale to industrial scale. There's steps, usually a factor of 10 that you're going to go. So this is the next one. All right, I want to say a couple things about Everbat. Everbat has turned into a very useful tool for us. It's an R&D 100 winning model. It's a new way to think about recycling. And so the best, well, before I say that, let me say that if you look at the green rectangles in the flow sheet, I like to start at battery manufacturing, and we have tools actually at Argonne, BatPack and Greek. Greek is a well-known LCA tool. BatPack is a well-known battery performance and cost model. So with those two models already, we had the cost and environmental impact to make a brand new battery. We were looking at recycling processes, and then we have also cathode manufacturing processes. And so all we needed to do was add a couple more steps, and we had a complete recycling circular path. And you can, I'll show a slide in a couple slides from now on the output of the model, but it makes it really easy to look either wide angle to say, for example, design for recycle. It costs more to make a battery because it has a easily undoable part. So you spend more, but then you can see in the recycling process or add up all the others to see how it changes. You can see that maybe it costs $1 more to make a battery, but if you go through the recycling process, you'll save $2. And so it does make sense. And so it helps you visualize that. You can also look really deep down and say, I have a new recycling process. I want to compare it to others. So you can model the different processes in the recycling process. So things like that. The biggest example of a reward that it made that I always think of is a recycling project was being reviewed through Everbat to find out how it was performing. And they found that a lot of the cost was from a solvent that was being used. And so looking through the data, they said, hey, why is this the biggest contributing factor? It seems so simple, but for whatever reason it was. And so the team that was doing the work on the experiment said, we don't need to use that solvent. We can use this one. And it changes things a little bit. And lo and behold, they saved a lot of money and a lot of emissions by finding this out. So it was so important. It's really neat how it worked. So moving on, this is the input. The goal was to make it so it was easy enough for anyone to use, and you can see with the stars, those are the only inputs that you need to put in to get data out. But we also wanted to make it a powerful tool so you could dig deep into parameters, understanding. You can change really anything. And because it's Excel based and it's free to download, and we're here to help you use it, this can be a very sophisticated tool to help you develop cost and environmental impacts from battery recycling. It's actually done so well that we've started using it under the evergreen suite of models. So it can be a product, it could be a material, but if you look at similar model methodologies, you can develop similar results and help advance your research. The outputs are what I really like to see. So on the left one, let's just focus on that. Recycle, Tech 1, Tech 2, Tech 3. It says this is the cost to recycle Technology 1 and Technology 2 and Technology 3. This is the amount of energy and type of energy it requires to recycle those different technologies using those different technologies. How much water? And what are the emissions and CO2 emissions, greenhouse gas emissions? as well as criteria foods. So this, I think, you can put them side by side, and this can be manufacturing costs versus recycling costs. Compare anything that you want. And actually, to digress a little bit, we took that methodology, and now, just like we do in some of the recycling processes, we have the impact model, which is for manufacturing and process assessments. This is for advanced manufacturing, but it does the same thing. Cost and environmental outputs are all the same, and the inputs will be different because it's a different process. But this helps us as a research institution better advance process technologies. And we have, as I mentioned, the ReCell industry. As I mentioned, the group works with industry so closely. So it was interrupted by COVID, but I'll call it annually. And we have one coming up in May, an industry collaboration meeting. And this gets all the different stakeholders together to hear everybody's perspectives and challenges and thoughts, really to hopefully break down the barriers and that not get you to focus on your problem, but to learn about others and how you can help them. And it gets you in the mix of a bunch of people that you can make new contacts with. So this has been great. It had, I forget, it was about 180 folks that came to this last one in April of 23. And that was from just under 100 different institutions. So it's a good mix of people. I'd like to acknowledge, first off, the Vehicle Technologies Office from the Department of Energy, and all the folks that work and contribute to the work that we do in ReCell. I'm sure this is not up to date. We have people coming in all the time, some people leaving. But here you go. We do have a web page. It is recellcenter.org that you can visit. And if you are interested in getting information about the industry collaboration meeting, you can put your email address information into on the right side of the homepage. I forget what they call it, but to get newsletters or something like that. My email is on the bottom right, and that is all I have for you. I would love to answer some questions, and I hope you enjoy the presentation.
Lovely. Thank you so much for that comprehensive talk, Jeff. As with all the talks, we are likely going to have lots of questions from the audience, and I can see that we have received some questions already, so I'll move straight into the Q&A now. So our first question that we have is, why is it that lithium-ion batteries die, and how does direct recycling address those causes?
Yeah, so there's a few reasons. One is, I mentioned earlier, the fact that you don't have as much lithium to cycle back and forth. That's because the lithium gets tied up in side reactions, creating unusable lithium compounds. And so what we do to mitigate that is we re-lithiate. When we get a cathode separated and ready to go, one of the last steps is to re-lithiate it. And we have, I think, 5 projects right now working to come up with the best alternatives to re-lithiate. Another one is, let's see, cracking. So it could be that the particles, these are polycrystalline particles in a cathode, and they can crack just from stresses, mechanical stresses. And so part of the processing that we do is to actually mend those cracks. They can add resistance so that material or electricity can flow. Let's see, another one, let's see, would be, there is coatings, there's layers that are generated on the anode and the cathode. So they basically need to be, I'll simply say washed. And so that's a part of the processing that we do to remove those which create an electrical resistance, which makes the battery less efficient. So there you go.
Lovely, a really interesting answer there, Jeff. Thank you. Our next question that we have had come in is, which of those recycling processes is the best for the environment?
That's a great question. My answer is all of the above. First, mining, refining, processing, manufacturing, all of those are worse than any of the recycling technologies that are out there. So you can't lose if you recycle it. If you're recycling responsibly, I guess you could potentially do it other ways, but no one does. So hydro, pyro, direct, they're all better than not recycling at all. Each of the processes has its benefits and its deficits. And so it depends on, I guess, a case-by-case basis as far as which is the best method to use, but they're all better than not recycling at all.
That's a really excellent point to consider there, I think. And following on from that as well, is there ever a time when recycling something doesn't make sense in the battery industry?
Yeah, there are times when you shouldn't recycle. It all comes down to life cycle analysis, or LCA. Sometimes, for example, transportation could be the killer for the environment. You could have something that's really valuable material, and you'd think are really costly or something, and so you might want to pick it that you would want to use that to recycle. And this is true with batteries. You may have to, because of whatever reason, drive it around. And a quick example is paper or plastic for recycling or for use in grocery store bags. So plastic, we use so much plastic and all that. But when you think about how much weight of food you can carry per pound of plastic, it's a lot less plastic weight than paper weight. And so you have to transport these bags. How far do you have to transport them? Are they made locally next door? Are they made across the country or across the world? And so there's a lot of thought that needs to go into the big picture. It all comes down to the big picture. So, so I would recommend we recycle as much as we can. That makes sense. Sometimes it doesn't make sense to recycle everything. But that is my answer.
Thank you so much for that. There's definitely a lot of things that we have to consider. And I think we've got one more question that we have time for today. And I think that's a really, really good one following on from that, because obviously we can see recycling is very important, no matter which option that we take for it. So what can each of us do to make sure that our batteries are recycled properly?
Perfect. So we all need to take part in the battery recycling. If we don't, and this is actually confusing, and we're working to improve it. A lot of people are working to improve it. If you look at a lithium-ion battery, it'll have an X through a garbage can. It says, don't throw it in the garbage. And then there's a chasing arrows, recycling. And so a lot of people put it in their blue bin, thinking they're doing the right thing, and it goes to the wrong place. It goes to a municipal recycling facility, which isn't made to handle batteries. It needs to go to a battery recycling facility. So make sure that you understand who collects batteries in your location. You want to research it. You want to ask questions. Don't just throw it in your blue bin. And I'm talking about consumer electronics, right? Your vehicles are going to go through a pretty good infrastructure for vehicle recycling. So there's not much you need to do there, but I'm talking more about your consumer electronics. But yes, it's very important that everybody knows where to take their batteries and follows through and takes them to that place. Thank you.
Excellent. I'll definitely be looking into where I need to take my batteries after that talk. Thank you so much, Jeff. Unfortunately, that's all we do have time for today. Any questions that we didn't have time to get to will be sent to the speaker after the event for him to answer. As with all the other talks in this event, this talk will now be available to view whenever you want for the next 30 days. And that just leaves me to say thanks again, Jeff. And for everyone watching, we'll be back soon with the next talk.
Thank you.